Today on Under the Big Tree, the Kyma International Sound Symposium 2018 keynote address, Altered States.
In the basement of one of the country's leading medical schools, Dr. Edward Jessup, candidate for a Nobel Prize, is conducting the most dangerous experiment in the history of science. And the subject of the experiment is himself.
Ask him what kind of an experience I can expect.
The noise is deafening.
He's blacked out.
What happens during these blackout periods is you get the feeling of phenomenal acceleration, like you're being shot out over millions, billions of years. Time simply obliterates.
You guys are shooting off with an untested drug that stacks up in the brain and works in the nucleus of the cell, and you don't call that dangerous.
I'm asking you to put the experiment off until we understand a little more in order to minimize the risk.
No way.
I'm really frightened. We could be screwing around with his whole genetic structure. Now, how do we stop this?
We've got millions of years stored away in that computer bank we call our minds. We have got trillions of dormant genes in us, our whole evolutionary past. Perhaps I've tapped into that.
He may be onto something that is beyond our own comprehension. Now, because I believe him, I want this thing stopped.
The hell was that?
You okay?
If you love me, Eddie, defy it!
Altered States.
They're trying to understand the relationship between the activities of the human mind and the physiologic activities occurring in the associated brain body. One of the UVA researchers is a psychiatrist, Kim Penberthy, and she recently got a grant to study deep meditators. While it's well known that meditation can reduce stress and enhance people's overall quality of life, there have also been some anecdotal reports of unusual experiences occurring during or after meditation. Things like precognition or telepathy, clairvoyance, increased synchronicities, memories of past lives, and out-of-body experiences. And they are currently looking for volunteers for the study. So if you have any of these experiences and want to participate, go to their website. An open, informed study of all aspects of consciousness. In it, he says, science thrives when there's an open, informed discussion of all evidence and recognition that scientific knowledge is provisional and subject to revision. This attitude is in stark contrast with reaching conclusions based solely on a previously held set of beliefs and the assertion of authority figures. Evidence is also the goal of Timo Thorsten Schmidt's research. Schmidt is a neuroscientist at the Free University Berlin who uses neuroimaging to study the underpinnings of human consciousness, especially the mechanisms underlying altered states of consciousness. Schmidt wants to map subjective experience to physical brain function. So he's building an online database called the Altered States Database, ASDB. It's online. It is available already. And he's amassing scientific data from peer-reviewed Medline-listed studies, documenting the subjective effects of different mind-altering techniques. Anything from different drugs to meditation to sensory deprivation, and then cross-correlating these subjective effects with what is actually going on in the brain at the same time. By consolidating the data from multiple studies in a single database and encouraging researchers to standardize questionnaires to capture the dimensions of subjective experience, Schmidt hopes to come to a better understanding of which brain activities are correlated with which subjective experiences. The Altered States database is just the first step toward a new field of study that Schmidt calls phenomenoconnectomics, the study of brain connectivity in relation to the phenomenologic state of consciousness. By combining techniques borrowed from big data and computational modeling, Schmidt thinks it will be possible to discover new ways of treating mental illness. If altered states of consciousness have an underlying structure of experience and common underlying brain mechanisms, then studying them concurrently might allow us to make a mapping between them. An altered state of consciousness is a multidimensional phenomenon. It's not just one aspect of consciousness that gets multiple aspects of consciousness are altered in varying degrees. So researchers use a standardized questionnaire to try to capture and compare people's subjective experiences along these 11 dimensions, some of which are an experience of unity, a sense of disembodiment, or audiovisual synesthesia. Schmidt's database is organized by induction method. So for example, if you search in the ASC database for LSD, you can combine these 11 dimensions of subjective experience across 6 different studies that were undertaken between 2015 and 2017, and correlate them with the associated neuroimaging data from the same studies. And this is part of the page showing how to extract the 11 dimensions from the questions in the questionnaire. I was disappointed to discover that music is not one of the induction techniques listed in the database, at least not yet. Because it seems to me that music can also induce feelings of oneness and awe and bliss. And that music for game or film modulates the meaningfulness and emotions associated with characters and events in the story. And even walking around listening to your music over earbuds changes the way everything looks and feels. And it seems even to suffuse ordinary places and events with special meaning. So maybe it's up to all of us to try to do some interdisciplinary studies on this, and on the ways that sound and music can induce altered states of consciousness. And make sure they're published in Medline-listed journals so that Timo Schmidt will include them in his database. So there are any number of ways to induce an altered state, and these are just a few of them. Of course, the obvious one everyone thinks of first is drugs, which to grossly oversimplify, are chemicals that insert themselves into the connections between neurons and act either by increasing the production of a neurotransmitter, being similar enough to substitute for a neurotransmitter, or by blocking the function of a neurotransmitter by binding to the receptor sites that would normally be the binding sites for that neurotransmitter. But drugs may not be the most effective way to induce altered states because chemicals take time to diffuse and it's not easy to spatially target their effects or limit their effects. So some researchers prefer to manipulate brain activity using electrical or magnetic or optical or ultrasonic signals. In fact, I found a whole subreddit that was devoted to building your own transcranial direct current stimulator. You should have 9-volt battery. But that entails passing direct current through your skull, and may not be that easy to pinpoint exactly which part of the brain is getting stimulated, and probably not possible to penetrate very deeply into the brain. Optogenetics is a technique that kind of hijacks the DNA of your nerve cells by inserting a short sequence of bacterial DNA that will synthesize light-sensitive protein, making it possible to switch that neuron on and off with great precision using pulses of LED light shining through a surgically implanted window in your skull. If you don't...
Sign me up.
If you don't relish the idea of modifying or putting a window into your skull, there's a less invasive technique called low-intensity focused ultrasound, or LIFU. With LIFU, you can use the mechanical vibrations of sound to modulate your brain activity, which has the advantage that it can be spatially focused with millimeter accuracy, and it can reach deeply into regions of the brain without surgery or genetic manipulation. Seong-Shik Yu at Harvard Medical School even used focused ultrasound to create a non-invasive brain-to-brain interface. So here, he's established a functional link between a human brain and the brain of a rat that's under anesthesia. When the human volunteer on the left sees a green circle on the screen, he lifts his left thumb. And the increased amplitude in the steady-state visual evoked potential triggers the focused ultrasound to modulate the rat's brain, causing the animal's tail to move. Some of the techniques for inducing altered states of consciousness have been around for thousands of years. In an interview published in the journal Anthropology of Consciousness, USC neuroscientist Antonio Damasio notes that cultures all over the world utilize breathing exercises, ritual drumming, yoga, meditation, dancing, fasting, and other techniques to induce altered states of consciousness. What all of these techniques seem to have in common is that you alter the physical state of the organism. For example, by changing the rhythm of respiration, you're also changing the proportion of CO2 to oxygen in your tissues. And since a large number of chemical processes depend on these proportions, you're changing the state of your body as a whole. Well, the heart, the lungs, the gut, the smooth muscle of the arteries. You're basically changing the internal chemistry of your cells. According to Damasio, an altered state of consciousness arises from an altered internal body state. It's the experience of deviation from homeostasis. Homeostasis is the tendency of living organisms to counteract temporarily limited perturbations in order to maintain stability. And in control theory, the usual way to try to maintain stability is with a negative feedback loop. When the input variable goes up, your control would go down to counteract it, and vice versa. So body temperature would be a familiar example. The hypothalamus is always monitoring perturbations in your internal temperature. And if your body temperature goes above normal, the brain triggers you to perspire to cause evaporation and cool your body back down. And if it drops below normal, it may trigger you to shiver and try to bring the temperature back up. And if you were to try to model this in Kyma, the input on the left could be the outside temperature, and it's feeding into a level, and the level will be either attenuated or boosted to make the current body temperature. On the bottom branch, you would take the difference between the desired body temperature and the current body temperature, and use the integral of the difference as a control. So that's the little red feedback there. That becomes the control signal on the input temperature. So it'll attenuate the input if it's high and boosted if it's low. So here, as we increase the input temperature, the control theta decreases. That's the negative feedback. So the current temperature, which is the theta right in the center, tends to hover or keep coming back to the ideal temperature that's on the theta right next to it. And even if I jerk the theta up and down, the negative feedback causes the current temperature to come back to the set point, or the normal temperature. So it maintains homeostasis in the face of these short-term deviations. But if I move the theta too far out of the operating range, like below freezing, there is a point at which it can no longer compensate, and then it flatlines. Which has some interesting parallels to the other theme of KISS 2018, ecosystems. If we define stability as the persistence of environmental conditions that allow for a widespread biosphere, then the Earth has demonstrated remarkable stability, a kind of a homeostasis, over the past 3.7 billion years or so. And this is in large part due to these multiple negative feedback loop systems, like a predator-prey system. And just the same as in the body temperature example, if you stray too far out of the operating region of the control system, you can also reach a point of no return. And then when that happens, both the predators and the prey die out. So we keep talking about states and homeostatic states, states of mind, inner states, altered states of consciousness. But what is meant by the word state? One of the dictionary definitions is conditions at a specific time, which kind of implies that state exists whether you're paying attention to it or not. For example, the physical states or phases of matter, things like solid, liquid, gas, or plasma, exist whether you're paying attention to them or not, kind of like the proverbial tree in the forest, falling in the forest. But to me, memory is something a little bit more than that. Memory is a state that you can intentionally change and intentionally measure or read back at a later time. In other words, it's like a state that you can alter and then read back at will. NYU neuroscientists Nikolai Kukushkin and Thomas Carew define biological memory as any perturbation in a system caused by external stimulation which exists or persists past the cessation of the initial stimulation and alters the system's responsiveness to subsequent stimulation. And at UCSD, there's some physicists, Massimiliano Di Ventra and Fabio Traversa, and they have this really cool, very succinct definition. Memory is a time non-locality. In other words, memory gives you access to information from the past. But I think in their definition, it could be from the future, because they didn't say. But it gives you access to signals that are not currently present. So how could we make a memory? So you could create a dynamical system with two stable equilibrium states, and then push the system into one state or the other, and it would stay there even after you stopped pushing. Or you could go with Di Ventra's definition of a time non-locality and use a delay line. In other words, you could exploit propagation delay of sound and kind of create a time non-locality out of a spatial non-locality. You could change the phase or the state of some material. You could increase the temperature to change a solid to a liquid. You could change the quantity of something in a container, for instance, by increasing the number of electrons in a capacitor or changing the relative concentration of proteins in a living cell. Or you could change the shape of something. Maybe something like moving a bead on an abacus. Maybe it's changing the shape of something to make a memory. Or changing the sequence or position of base pairs in a DNA molecule. And there are probably others, too. Which brings us to an important anniversary. This June, 2018, was the 100th anniversary of the invention of the first electronic flip-flop. William Eccles and F.W. Jordan applied for the patent 100 years ago this summer, but it probably didn't look like these. Eccles and Jordan's flip-flop might have looked something like this, apart from the 9-volt batteries. In the May 2018 issue of Active Spectrum, Richard Brewster describes trying to build a flip-flop using the kinds of parts that Eccles and Jordan might have had available to them at that time in 1918. And it turned out to be a pretty challenging project. They had a hard time fine-tuning it to actually get it to work as a flip-flop. A flip-flop is an electronic toggle that stays on or off even after the initial electrical control signal has ceased, which sounds a lot like Kukushkin and Caru's definition of biological memory, something that retains its state after the original signal is gone. A flip-flop is a bistability, meaning it's a dynamical system that has two equilibrium states. So it's an example of the first way we came up with for making a memory. You can build a flip-flop out of any two cross-coupled inverting elements, like vacuum tubes or bipolar transistors. But for non-analog people like me, it's easier to imagine it with NOR gates. So NOR just stands for not or. And so if you imagine the truth table of an OR gate, if either of the inputs is 1, the output of the OR gate is 1. So there's actually only one false case, and that's when both inputs are 0. And so the NOR is just the opposite of that. There's only one true case. There's only one case when the output's 1, and that's when both inputs are 0. So in a way, the NOR is kind of a detector for both inputs being 0. So now imagine two NOR gates, cross-coupled so the output of each is used as the input to one of the inputs to the other. So in this picture, the red lines are 1s and the black lines are 0. The bottom input is labeled S for set, and the top input is labeled R for reset. And the output of the flip-flop is Q, and there's also a not Q, the opposite of the output. Okay, so let's set the control signal S to 1, for red. The output of the bottom NOR becomes 0, and that output feeds back to become the second input to the upper NOR gate. Since both the R input and the fed back input are 0s, we have the magical case of 2 zeros, and so the output of the whole flip-flop becomes a 1. And the output of the upper NOR gate also feeds back to become the second input to the lower NOR gate. And since both inputs to the lower NOR gate are 1, the lower output of the lower NOR gate is 0. Now let's switch off the S input, changing it from 1 to 0. Even after you remove the control signal from S, the value of Q still sticks at 1. And it's this persistence of the value, even after that original input has been removed, that makes it a memory. The only way you can reset the flip-flop is by setting the R, the reset, to 1. I'm not sure whether Eccles and Jordan actually thought of their invention as an electronic memory back in 1918. Because in the paper they published about it in Radio Review, they describe it as a trigger relay. A one-stroke relay which, when operated by a small triggering electrical impulse, undergoes great changes in regard to its electrical equilibrium and then remains in a new condition until reset. About 20 years later, a physicist at Iowa State University named John Atanasoff was inspired by the flip-flop to start thinking about a new kind of computing machine. One night in 1937, he was feeling frustrated about the way his research was going and he needed a drink. But Iowa was a dry state, so he got in his car and started driving 100 miles per hour toward the Iowa-Illinois border. 2 hours later, he stopped just across the border. He stopped in an Illinois roadhouse and ordered a bourbon and soda. And he started sketching out some ideas on a cocktail napkin for an electronically operated computer machine. Atanasoff's back of the napkin sketch for this new computing machine used base 2, or binary numbers, instead of the traditional base 10 numbers. It would compute using logic instead of the enumeration techniques that were used by analog calculators. And it would use condensers or capacitors for memory and have a regenerative process to refresh the memory. So this is a case where coming up with a new computing paradigm required someone to alter their state from Iowa to Illinois. So they could induce an altered state of consciousness by ingesting ethanol. After he got home, Atanasoff put his ideas into a patent application and submitted it to the Iowa State administration. But the paperwork just sat on someone's desk, and the university never filed for the patent. It's hard to overstate the impact that the invention of an electronic flip-flop had on the evolution of computing. Without the flip-flop, you can still design circuits that do combinational logic, where the output depends on the current inputs. But an electronic memory is what made it possible to perform sequential logic. It meant you could construct a sequence of operations, each of which could depend on previous results, which is the way that most of us were taught to think about what is an algorithm, or what is computing, as a sequence of steps, some of which include intermediate stores into memory or reading out of memory. So in some sense, what we call computing is the process of sequentially altering states. By the early 1940s, people had started building electronic computers that could perform sequences of steps that could be programmed by means of switches and patch cords, and eventually by means of machine languages and higher level languages. In all likelihood, we wouldn't even be here today at KISS 2018 making sound and music with our Pakaranas and with Kyma if it were not for the invention of the electronic flip-flop 100 years ago. Thanks. One of the first computer memories I found out was actually based on an acoustic delay line. The Electronic Delay Storage Automatic Calculator, or EDSAC, constructed by Morris Wilks at Cambridge in 1949, had memory based on the propagation delay of acoustic signals through tubes of mercury. So this could be an example of that second way we came up with for creating a memory, using propagation delay to create a time non-locality. In the EDSAC memory, a piezoelectric transducer would convert an electrical pulse into a sound pulse, which was then transmitted as a sound wave through a tube filled with mercury. It was detected at the other end, at which point it could either be changed or refreshed and sent back. So in this way, the EDSAC memory could keep bits circulating in the mercury at all times. The EDSAC required 32 tubes of mercury, each of which was 5 feet long, and the mercury was rather expensive. In his Turing Awards speech in 1967, the now Sir Morris Wilks recalled that Alan Turing had proposed a cheaper substitute for mercury as the propagation medium. Apparently, Turing advocated the use of gin, which he said contained alcohol and water in just the right proportions to give zero temperature coefficient of propagation velocity at room temperature. And they did confirm that that was true. This is a photo of the mercury delay line memory of a 1951 computer called the Univac. You could call this serial access memory, or SAM, instead of RAM. To access the memory, you would ask for an address or pulse number, and then wait for that pulse to propagate through the tube. Once the pulse arrived at the reader end of the tube, it could be accessed. And the access time for any particular bit was approximately 0.2 milliseconds, which was faster than I expected. One of the earliest forms of random access memory, or RAM, was an interconnected grid of ferrite rings called a magnetic core memory. The rectangular grid made it possible to address the ring at any XY location at any given time. So you could access any bit at random. Magnetic core memory works by changing the state of a ferrite ring or core by causing the magnetic moments of the atoms in the metal to align with each other in the same direction. So this is an example of that third way of making memory by changing the actual physical state or phase of the material. There's a wire wrapped around each core, and when current flows in one direction through the wire, it magnetizes the core in one direction to represent a 1. And then if you change the current flow direction, it would cause, in the opposite direction, it will cause it to magnetize in the opposite direction. And you could use that to represent 0. To read the magnetic core, you would write a 0 to it. And it would, if there was a 1, it would flip. And that would induce a current in the second wire, the read wire. And so you'd get a little electrical pulse that said, oh, this used to be a 1. And if it was already 0 and you read a 0, nothing would happen. So it was a destructive read. But if you didn't read it and you would just left it the way it was and pull out the power, it actually will stay in its state indefinitely. And magnetic recording tape operated on a very similar principle by changing the state of the oxide particles on the tape. The DRAM that you have on your laptops and Pacaranas works by charging up rectangular grids of tiny capacitors with electrons. So when the blue switch in the diagram on the right closes, current can flow in and electrons fill up that purple capacitor almost like marbles rolling into a cup. So in this kind of a memory, when the number of electrons exceeds a threshold, it's interpreted as a 1. And if it's below the threshold, you'd interpret it as a 0. But DRAM also does destructive reads, and the capacitors are leaky, so you have to periodically refresh the charge on the whole grid. And as you well know, when you pull the power, anything that was in the DRAM will go away. So DRAM, we could say, is an example of that fourth way of creating memory, by changing the quantity of something in the container. In this case, the container is a capacitor, and we're changing the number of electrons in the capacitor. There's another class of electronic memory, which is actually a combination of an electronic component and a memory, as reflected in their names. Memristors, memcapacitors, and memductors. One of these, the memristor, is a kind of a nonlinear resistor that has state. And one of the hallmarks of a memristor is its so-called pinched hysteresis curve. So with a normal resistor, if you were to plot the input voltage against the output current, the result would be that straight green line. With a memristor, you would see that at large enough positive voltages, its resistance will drop, and it lets more current flow to the output. And once it's in that state, even when you lower the voltage again, that left going red arrow, it will kind of stick with its low resistance value until you get really, really far into the negative before it would go back to the high resistance again. So that's what gives it that pinched hysteresis plot. So here's a Kyma sound that will demonstrate the behavior of a memristor. The sound uses an input-output characteristic for the nonlinearity and a lossy integrator to simulate the state change in terms of conductance, and an inverted scale and offset to convert the conductance to resistance. Okay, so here is that hysteresis curve for low, and this is for a higher voltage. And then when you exceed the threshold, you see now it's got two choices. And it follows one straight line slope as you increase the voltage, and when you as you decrease the voltage, it follows a different path. So you're following a different straight line slope as you decrease the voltage. So you could use those two different resistance states of a memristor to represent a 1 and a 0, so as a memory. To set the memristor to a high resistance, I'll demonstrate that here. You send it positive voltage pulses, very large ones. And then if you look at the input and compare the input to the output at the top, you can see the output on the right is attenuated by the high resistance. To set the memristor to a low resistance, you would send it big negative voltage pulses. So you have now a kind of a resistor where the memory is actually part of the resistor. At the time when the first electronic computers were being built, around 1947, John von Neumann came up with a computer architecture that's still in use today, where the memory is separate from the arithmetic logic unit, or the ALU. And to this day, pretty much any processor that's in widespread use, whether it's the processor in your laptop or even the processor in your phone, both of those processors use this same architecture, even though it's like 70 years old. But over the course of the last 70 years, computation times have been getting faster and faster, but the memory access times haven't been keeping up, leading to a kind of a bottleneck between the memory and the arithmetic logic unit. And not only do the memory accesses slow down computation, the energy consumed by DRAM is a significant part of the total energy consumption of any processor. So until we can figure out a way to overcome the so-called von Neumann bottleneck, Moore's law is now pretty much at a plateau, and it's going to be stuck there until we can overcome that. One possible way around the bottleneck is to use grids of stateful components like memristors to perform sequential logic in the components themselves, storing the intermediate states in the components, rather than moving the data out to memory and back in. That's the idea behind the MEM computer, which is a new model of computation being developed by Massimiliano Di Ventra and Fabio Traversa at UCSD. Unlike the von Neumann architecture, where the memory is separate from the ALU, the MEM computer does logic computations in the memory itself. And there is no separate memory, so there's no more bottleneck. And in that respect, the MEM computer has something in common with the human brain, in that it can both compute and store using the same hardware. So what about that last way, which was to encode a memory by changing the shape of something? That might be the best way to characterize the use of DNA as a memory, since it involves changing the position and sequence of base pairs. Last year, Seth Shipman and others at Harvard Medical School reported that they had successfully stored and played back a 5-frame movie in bacterial DNA. They used CRISPR to encode 5 frames of a racehorse in motion, 1 frame per day, over 5 days. Afterward, they were able to reconstruct the frames with 90% accuracy by sequencing the DNA. And the movie survived over several cell generations. The idea is obviously not to use DNA to store GIFs, but to demonstrate a way to track and record events, dynamic events within a cell, by getting the cells themselves to record what's going on at a molecular level. As Shipman puts it, we want to turn cells into historians. But they are already, aren't they? In a way, isn't our DNA a memory of every challenge, every deviation from homeostasis ever encountered by living organisms on the earth, since the origin of life, or perhaps even earlier? Sort of like in Ken Russell's film, where the protagonist is accessing billions of years of evolution and memory in his DNA. So it seems like almost anything can be used as a memory. Propagation delays, changing the state from solid to liquid, charging up a capacitor, or even folding or otherwise modifying the shape of a physical object. This is from a paper published in Nature last year on using origami-based tunable structures to construct a non-volatile mechanical memory. What all these approaches seem to have in common is that they involve making some kind of an analogy, or a mapping, or a transduction from one kind of energy or physical configuration to another, and doing it in such a way that the target of the mapping persists even after you remove the original. So how does the brain do this? How does a brain make a memory? This is an image from Steve Ramirez's lab at Boston University that was on the cover of Science in 2013. The red cells are memory engram-bearing cells in a mouse hippocampus. Engram is a term that was actually coined by a German zoologist in 1921, and it's a term that also became an important part of the Star Trek canon. In current usage, engram cells are those cells that are active and undergo permanent changes during memory formation and recall. An engram, or a memory, doesn't have a single spatial position in the brain. It's more like the coordinated activity of an ensemble of cells that are spread throughout the brain. In the 1940s, also around the same time the first electronic computers were being built, psychologist Donald Hebb came up with this catchy little maxim describing the formation of biological memories. Neurons that fire together, wire together. It's these assemblies of cells firing together that are known as engrams. The process of memory formation, otherwise known as learning, is a strengthening of the connections or synapses between neurons, leading to the development of these brain-wide assemblies of cells. Not only are the cells physically connected to each other, they also start to coordinate their activities. So an engram is almost like a musical ensemble of cells. It may be that our brains use a combination of all of those techniques that we listed for making a memory, because it's kind of changing the shape, and then it's changing the way the network is connected, maybe changing the levels of relative concentrations of proteins in the cells. But maybe it also has a new way that we didn't mention, which was synchronizing across the brain, almost like synced oscillators. In her 2015 paper, Finding the Engram, Sheena Jocelyn and colleagues at the University of Toronto were able to demonstrate Hebb's principle in mice. Using optogenetics, they found evidence of the same assemblies of hippocampal cells firing together during both learning and retrieval of a memory. And optogenetics is the technique of using light to modulate molecular events in specific targeted cell types within a living organism. It works by taking the genetic code for a light-sensitive protein called an opsin from green algae and using a virus to insert that bit of genetic code into the mammalian cells that you want to study. And then once that's done, the researcher can switch on and off those cells using pulses of LED blue light. In 2012, Susumu Tonegawa's lab at MIT developed a clever way of using optogenetics to also label the engram cells involved in encoding a specific memory. So while it's happening, they are labeling which cells are active. That enabled them to be able to trace both the storage and the retrieval circuits for that specific memory. So I'm sorry to say that most of these studies, all the ones I read, involve fear memory. And I think it's because mice react to fear by freezing up. And so that makes it easy for them to tell both when the mouse is afraid and also if the mouse remembers being afraid, because they will act the same way. So using optogenetics to label the cells involved in a fear memory and then using light pulses to reactivate the memories, first 1 day later and then 2 weeks later, Tonegawa's lab found out that memory is formed rapidly and simultaneously in both the prefrontal cortex and the hippocampus. But that over time, the engram in the prefrontal cortex grows stronger while the engram in the hippocampus grows weaker. So on the computer, we're always moving data around. So we maybe use short-term value we would put into a register, and medium term we might put it into DRAM. And then for the longer term, we would move it to the SSD. But it appears that biological memory engrams are formed immediately in several places throughout the brain, and that the engrams then develop and change character over time. There is no transferring of memories from a short-term storage place to a different place. It's just in one place. So they seem to be distributed and linked to each other by synchronous nerve firing patterns. And once formed, they don't seem to move around. A new experience induces protein synthesis and new connections in the brain. Some of the proteins have to be synthesized quickly in order to make an association with an event and a specific context or location, while other proteins take longer to be expressed. MIT neuroscientist Wei-Feng Xu puts it, novel experience induces changes in neuronal protein content and synaptic strength, which eventually leads to memory encoding via long-lasting modifications of a pattern of neural connectivity. In other words, warning, these new experiences may result in long-lasting alterations to the state of your brain. These changes may persist over several hours, weeks, or even the lifespan of the organism, or perhaps even longer. Researchers at Emory University have seen evidence that fear memories can be passed down epigenetically to first and second generation offspring. Brian Diaz and Kerry Ressler exposed mice to acetophenone, which is the smell of cherries and almonds, while delivering a mild electric shock to their feet. So the mice learned to associate the smell of cherry almonds with a shock. And from then on, they would shudder in the presence of the smell, even if they didn't get a shock. But the weird thing is that the behavior was passed down to their pups, who would also shudder in the presence of that smell, and even to the grandchildren. So Diaz and Ressler believe that traumatic memories may be passed down through a process of epigenetics, or DNA methylation, which is a reversible chemical modification to DNA that can block the transcription of a gene without actually altering the sequence. Using optogenetics, researchers have been able to reactivate memories, and they're also starting to investigate techniques for suppressing memories, or even for creating false memories. Steve Ramirez, the neuroscientist at Boston University, posted this manifesto on his lab website. Hidden between your ears is a time machine. In the lab, we will break into this time machine, reverse engineer it, and ultimately control it. It's not a matter of if, it's a matter of when and how. In his 2013 paper, Creating a False Memory in the Hippocampus, Ramirez describes how he created a false fear memory with optogenetics. Like all of these other studies, it starts out by putting a mouse in a chamber and delivering mild electric shock through the floor to create a fear memory, while tagging the implicated memory engram cells with a light-sensitive protein. Next, Ramirez put the mouse in a new chamber, and he activated the fear memory artificially in the new context using optogenetics. From then on, when the mouse was put in the new chamber, it would freeze in fear, even though it had never been delivered a shock in that chamber. So Ramirez had created a false association or false memory of having been shocked in that new location. Nikolai Kukushkin and Thomas Carew at the NYU Center for Neuroscience published an extensive review last year called Memory Takes Time. And I think the reason I like it so much is because the way they describe memory sounds as if they were describing music. They describe biological memory as a holistic, hierarchically structured system that represents the timing of past events, where levels of the hierarchical system are linked to each other through both coincidence detection and feedback. A key feature of this system is the possibility of representing multiple timescales of past experience that span from milliseconds to years. In other words, the structure of memory, like the structure of music, lies in the temporal domain. Kukushkin and Carew define experience as a series of temporally limited deviations from homeostasis, the timing of which determines the structure of the resulting memory, which sounds a lot like the way we experience music, as a sequence of temporally limited deviations, the timing of which determines the structure of the music. They also conclude that the biological utility of memory stems from its ability to modify future behavior based on past events, which may explain why we feel driven to seek out novel experiences and altered states. Maybe because those of our ancestors who were curious were better at learning how to survive and thrive in the face of new challenges. And aren't we ourselves a series of temporally limited deviations from the homeostasis of the universe? So by that definition, are we the experience of the universe? Even the most ardent materialist will agree that our state and our memories, personal, genetic, and cultural, are a constant source of non-locality, time non-locality in the universe. And that we are continuously translating and mapping the patterns of neuron firing and protein synthesis and connectivity that we call our memories into new physical, chemical, vibrational forms. Damasio points out that all living organisms, from single-cell bacteria to multicellular mammals, experience and remember disturbances to the homeostasis, and use those memories to survive and thrive in the future. But humans, perhaps more than any other animal, also, we seem driven to share our experiences and our memories, and to remap them to alternate, more persistent forms. Because through language and music, we're able to experience and form memories of events that we've never directly encountered. It may be part of why we felt driven to come here this week, to participate in a shared experience, to transfer some of our experience to those around us, and in turn to be transformed by the ideas and the music that we hear at the conference. And just as Steve Ramirez is creating false memories in mice, all of you, as artists and engineers, are masters at creating experiences that never happen to anyone ever, and using technology to make those experiences into actual, real, physical experiences that others can store and recall as memories. Last year's KISS organizer, Joran Rudi, told me that the first time that he visited New York City, he had this strong feeling of coming home. And it wasn't because he had past life memory or anything. He'd just seen so many movies and TV shows that were based in New York. And they had become an actual part of his childhood memories. So in the same way, the memories that you create will get mixed in with memories of actual events and the stream of current events, and are shaping the future state of the universe. So perhaps we should conclude with a warning. Over the next few days, you may encounter novel experiences. Novel experiences have been shown to result in physical alterations to the state of the central nervous system. These alterations may persist over time intervals ranging from milliseconds to hours to days to your lifespan and beyond. Welcome.